Hi viewers, welcome to LMS Solution. Today we are going to see about the control of UPQC by using two control method. One is a DQ0 for a series active filter as well as shunt active filter, and we have another control logic, that means DQ0 control logic for a series active filter and a PQ control concept for a shunt active filter. And then we are going to compare these both control logic in terms of THT and then mitigation of voltage sag and swirl concept. So this is a simulation model we developed for that UPQC. We have source, grid source. Grid source voltage is 400 volt, 50 hertz, and here we have created that sag. Here you can see that at 0.4 to 0.5 second we created the voltage amplitude equal to 0.7. That means here we are creating 0.3 per unit voltage sag, and then from 0.6 to 0.7 we are creating 1.3 per unit. That means we are creating 0.3 per unit for a voltage swirl. And also here we are creating a harmonic in the grid source from 0.2 to 0.3 second. That means we are adding a fifth harmonic and seventh harmonic in the grid side, and this is known as series. That means transformer, injecting transformer is connected in series in the line, and here we have a non-linear load. Okay, so this non-linear load will be create the harmonic in the source current. Okay, so here we are creating sag swirl harmonic in the source voltage, and then by means of nonlinear load it's going to be create the harmonic in the source current. Okay, so this is going to be controlled by means of series active power filter and shunt active power filter of the UPQC. So here we have that series active power filter inverter. So this inverter going to be controlled by means of DQ0 control. So here you can see that. So this is a control logic of that DQ0 in the series active filter in the UPQC. So we need to measure the source voltage, load voltage, and it's going to be converted into DQ0. So here we have to use PLL for generating omega t. Okay, so this is going to be given to this ABC to DQ0 block. Okay, in order to convert that ABC to DQ0, and then here you have to take only T and Q quantity of source, grid voltage and load voltage, and then here you have to compare. Okay, so after comparing we will get the error voltage and also the load voltage of D and Q axis, right? So it's going to be compared with the some rough constant 0, 327. Okay, after that you will get some error. Okay, this error, right, both error, right, this one and this one and this one. Okay, so going to be compared here, and it going to be processed by a PA controller. So this PA controller will be generate the control signal, so based upon the error voltage, okay, in the form of D and Q axis. And then so this is going to be processed via DQ0 to ABC, and then so the final ABC, right, it's going to be processed via PWM generator. Okay, this one. So it's going to be processed via PWM generator, and then it's going to be given to that when the pulse from that PWM generator is given to this voltage source inverter of the series active power filter, not to mitigate that problem of sag swirl and the harmonic in the source voltage or grid voltage. So next you need to see about that control logic for a voltage source inverter of this inductive filter. So here we are going to measure load current, and that load current will be converted into DQ0, and then here you are going to consider only D and Q. So here you can see that here we are going to apply low pass filter not to take that mean average value of that D axis, that means load D axis current, and then finally is subtracted with the actual. And then here you can see that, so here you need to measure DC link voltage, that means here we need to measure the DC link voltage, and when we compare with the reference voltage 700, it process by PA controller, so it will generate the loss power. So this power going to be, so loss power or loss current, it going to be separated with this output, right? And then it going to be converted into ABC by using this DQ0 to ABC. Okay, so here only we are applying that harmonic elimination concept. So based upon that loss power current, and then a real power, right? So you have to generate a reference current. So after that, this reference current going to be compared with that voltage source inverter of this unactive, that means current of the voltage source inverter of this active power filter, and process by series controller, and then it will be generate the pulse. So this pulse going to be control this voltage source inverter of this unactive filter. Okay, so this filter, right, unactive filter will be eliminate the harmonic problem in the because of this nonlinear load, right? So it going to be change the nature of the source current. Okay, so this is a DQ control we are applying in both the series active power filter and the shunt active power filter of the UPQC. And same way, so here we have this another model UPQC with the DQ not control in the series active power filter and PQ control in the shunt active power filter. So DQ not control, whatever control logic we saw before, right? So same control logic we implemented here for series active power filter, and for shunt active power filter, so here we are using that PQ control theory, that means you have to calculate real reactive power, 0 seconds real power, 0 seconds current, and then you have to apply that extraction of actual power, and then you have to calculate the loss power, right? Again this actual power going to be used for actual power, reactive power, and then 0 sequence power and current is going to be used for generating the reference current. Okay, so here we need to feed it source voltage and then load voltage. So based upon that you have to that means you have to calculate PQ, P0, I0. Okay, and same way, and then you have to apply this filtering concept, and then loss power subtraction, and then you have to apply here, we have to apply transformation, like we have to apply ABC to alpha naught, and then by using alpha beta quantity you have to calculate real and reactive power. So same way here we have to apply inverse PQ concept, that means from that to be ABC I0, I alpha, I beta, we have to calculate the reference current IAC, IBC, ICC. Okay, and then this reference current, right, going to be compared with the current of this inductive filter, and it's going to be processed by hysterics controller, and then it's going to be control this voltage source inverter of this inductive power filter. Okay, so here we apply that DQ0 for series active filter and PQ control concept for syntactic filter. So here also we are taking same control, that means operating condition for source side as well as load side. We are having nonlinear load. Okay, so you have to first time you want to simulate this model, and then you have to check the results. So first we need to load the data in the workspace. So not then only we can find out that TST. So now I am going to simulate this model. So this is grid voltage, this is load voltage, this is voltage injected into that line. So this is grid voltage, this is grid current. Okay. So here you can see that we are getting a sinusoidal waveform for source current, because here we are using a nonlinear load in the load side. So even though we are using nonlinear load, so source current is like sinusoidal. Okay, and then at the time 0.2 second rate, we are injecting harmonic in the source voltage. We will check the operation of UPQC. So here you can see that we are injecting the harmonics in the grid. So here you can see that it injecting some voltage in order to alleviate that problem. Here you can see that we are not get exact sinusoidal because of that harmonic problem. Okay, so but it reduces somewhat, right, by using that DQ0 control along with the PQ control in the syntactic filter. And also you can see that the source current, right, source current also having harmonic during that period, during harmonic injection in the source voltage. And then here you can see that sag is occurring in the 0.4 second because of that UPQC, that means series active filter is supplying some voltage in order to mitigate that problem. So voltage maintain at 230 volt phase to ground voltage, right? And then here you can see that, so this is a variation of source current also maintaining sinusoidal in sag voltage X also. Here you can see the voltage swell is occur at 0.6 second, and also UPQC is injecting some voltage in order to maintain load voltage constant. Here you can see that source current also maintaining sinusoidal nature, right? Here you can see that that for different scenario, right, for harmonic injection in the grid voltage sag or swell in the grid voltage, the UPQC is elevate that problem, but it have some problem in the during harmonic injection. So we can see that in the THT detail only. So I am stopping this simulation and go to in 2021. This model run at 2021A. So just go to open this out function and then click scope data and then enter here and click scope data 2 and then you type ANS1, enter. So after that comes to here and then open this Power GI and then click tools FFT. So here you can see that TST for the source current, load voltage. So So this is for a series active filter. So I'm taking on the load voltage. So here I'm going to fix 0.24 because in between 0.2 to 0.3 we are injecting harmonic in the source voltage. So we need to check that THT value. So here we are getting around 11.98 percentage for source, so 20.62 percentage, right? During harmonic source voltage having a THT around 20.62 percentage. After mitigation by using UPQC by means of the DQ0 and PQ control theory, so we are getting around 1.98 percentage. Okay, so it will be reduced around 9 percentage of THT by using this UPQC concept. Okay, and then I'm going to take source current, right? This is source current. I'm going to checking that THT during that harmonic injection it having 20.36 percentage. Okay, it's not reduced. The source current also having 20.6 percentage, 36 percentage. And I'm going to take the test the model for a sag and swell. So sag will be occur at 0.4 to 0.5. So I'm going to consider 0.44 and then check the THT. So THT is around 1 percentage, no problem. And voltage swell occur in between 1 second, we will check that one, 0.6 to 0.7. Okay, so here I'm going to pick 0.64 and check the THT. So THT around 2.91 percentage. So during voltage sag and swell, so load voltage THT is around less than 5 percentage only. For sag is around 1 percentage. For swell is around 2.91 percentage. But for current, right, source current is 0.64 for voltage swell, and then for voltage sag is around 0.98 percentage. For harmonic injection in the voltage is 20.36 percentage. So here you can see that the current, right, source current is not having good harmonics, right? Is around it have only 20.36 percentage, is more than 5 percentage, right? So this will affect the other kind of load also. Okay, so same thing I'm going to take the control, that means DQ control for both shunt active and series active filter, and I'm going to simulate this model. So first we need to store the data. It's already stored here. Okay, no problem. So now I'm going to simulate this model. So same operating condition, whatever condition we followed previously, so same condition is updated in this model also. So here we use DQ control for both series and inductive filter. You will see the response result of this model. So here you can see that the source current, right, is sinusoidal only, and then you can see that this is a grid voltage, load voltage, and the injection of voltage by means of UPQC in the line. So this is source voltage, source current, and then you can see that now system is under normal condition, operated with the nonlinear load. So source current nature is sinusoidal, so no problem. At the time of 0.2 second, so harmonic will be injected in the source voltage or grid voltage. So you will see the response of the system. So here you can see that here harmonic is injected, and then you can see that load voltage maintained constant, and also it have some sinusoidal nature only, voltage sinusoidal nature only, and also you can see that the current also having sinusoidal nature. So here you can see that the current nature is sinusoidal, but is not sinusoidal in the PQ control theory concept during that harmonic present in the grid voltage. Okay. So next go with the sag and swell. So now voltage sag is occur, and then UPQC is supplying some voltage in order to mitigate that sag problem. Here you can see that so current is maintained constant, right? So there is no deviation in the current, and also the nature also sinusoidal. There is no deviation. After at 0.6 seconds, voltage swell going to be occur in the grid voltage side. So you will check the response of UPQC. So here you can see that voltage swell is occur, and then UPQC is supplying some injection voltage now to mitigate the problem, and also you can see that so there is no deviation in the current, so current maintained constant, and also nature also sinusoidal. When comparing with that DQ control, that DQ not PQ control with this DQ control for both the shunt and series active filter, right? So it will be provide better result. So next we have to check the THT of the system, so then only you can conclude the result. So here I am going to stop the simulation and going to this out, and then I am going to paste in the command window, and then here I am going to take. So next I am going to use Power GI and then tools and go to FFT analysis. So here I am going to check the load voltage at the harmonic injection, so 0.24. So here you can see the THT around 4.26%, but in previous control method, right, the THT around the 11.93%. Okay, and here you can see that THT is less than 5% only, even though harmonic present in the system. And then I am going with the voltage sag condition and check the THT. So THT is 0.94%, so it's less than 5% only. And I am going to check the condition at the voltage swell. So here also you can say 2.83%, right? So here you can see that for harmonic injection voltage sag and swell, right, the THT is always less than 5% only. For harmonic injection, the THT around only point, I think 4.26%. During voltage sag is around 0.93%. During voltage swell, the THT around 2.93%. So is less than 5% only. Is follow the IEEE standard. So next I am going to check the THT of the current during harmonic injection. So here you can see that it is around only 0.14%. During sag is around 0.16%. During swell is around 0.23%, right? But in previous method is during harmonic injection, the THT around 20.98%, but here the THT around only 0.14%, right? So in all operating condition, the THT is comes under 5% only. By using this DQ not control method in both series active power filter and shunt active power filter is providing the better result, and then DQ not control in the series active filter and PQ control in the shunt active filter. So this is a comparison of these two control method in UPQC. So thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.